Hello class, welcome to our Combinatorics video for Monday, April 27th. Um, this is just a video, it's not really a lecture because today I'm just going to look at a few of the problems from the sample test and just go through the solutions that I've already posted for the sample test, just to maybe elaborate on those solutions a bit. So probably by the time you watch this video, the test will already have been posted, the test for Monday, April 27th, because that is going to go up at 8:30 a.m. and then you will return that to me right by 1 p.m. on Wednesday, April 29th. And then of course I'll grade that, and you can also submit on Wednesday if you want to homework number 7, which is optional, just if you want to improve your homework grade. And then our test is our final exam will be coming up quickly. That's going to be posted on Monday, May the 4th, and then that will be due back on Wednesday, May the 6th, right? If you choose to take the final exam. So remember, if you do not want to take the final exam, you can allow the average of your 3 midterm tests to substitute for your final exam score. So if you are if you are having trouble computing your grade with by substituting that midterm average for your final exam, if you're trying to make a decision about whether you want to take the final exam, please contact me, right, so we can discuss that. If you think there's any question about what your grade would be with that substitution. I will be holding my Zoom office hours next week, just like normal, so just the normal schedule. Monday, Wednesday at 3, and then Tuesday, Thursday at 9 a.m., and then Friday at 10. So you have plenty of opportunities to either Zoom with me, or you can just email me. Also, right? Don't, however, message me in Blackboard, because I'm not likely to see that. Message in time. So go ahead and give me just send me an email at my regular university email address, right? Okay, so we're getting close, right? Very close here to the end, right? We've only got a couple more things left to do, and so the main thing there is the test next week, right? Okay. All right. So let's look at just a few of the questions off of the sample test. So again, the solutions are posted, and those are pretty complete solutions, but I couldn't write down everything that I might have said about the solutions there. So I'm going to look at a few of these problems today, and then just try to, again, as I mentioned, just try to talk a little bit more through the solutions, so you'll understand them a little bit better when you look at what's posted, right? All right, so let's start here with this problem number 3. This is a very typical problem, an inclusion-exclusion problem, actually. So there are problems like this in the homework, and we've solved problems like this, right, almost throughout the course, but not always using inclusion and exclusion, right? So this has, how many ways can we distribute 10 Snickers bars, right? So of course Snickers bars are not distinguishable amongst 4 children, but the children we can distinguish, right? Okay. So 4 Snicker bars amongst 4 children, but we're going to make this restriction, right, to be fair here, that no child gets more than 3 Snickers bars, right? No child gets more than 3 Snickers bars. All right, so let's see how we can solve that problem. So here's what we're going to do. We're actually going to translate this situation into solutions to integer solutions to an equation. Okay, and so the way I do that is we're just going to use these subscripted variables here, x. So I'm going to let x of 1 be the number of candy bars that go for the first child, right? And then let x of 2 be the number of candy bars that we give to the second child, and then x of 3 is the number of candy bars for the third child, and then x of 4 is the number for the fourth child, right? Okay, so obviously these variables all have to be integers. We're not going to split a candy bar, and actually they're non-negative integers, right? And so when we add up those four variables, right, that has to add up to 10 because there are 10 Snickers bars, correct, that we're going to distribute. So what we're really doing here is we're solving, we're looking for the number of integer solutions, right, to an equation. Okay, so we've been talking about this sort of problem right now for several weeks, except we have some restrictions, right, on the solutions to this equation that we're going to accept. Of course, they have to all be non-negative, right? So all the variables have to be non-negative. So you've got that basic restriction, but also we have the restriction, right, that each of the variables has to be less than or equal to 3, right? Because we don't want to give any child too many of the candy bars, right? We don't want to show favoritism, right, and give one child too many of the candy bars, right? So we're looking for solutions to the equation, but with the restriction, right, that each of the variables here has to be less than or equal to 3. So we're going to solve this, though, kind of backwards, all right? We're going to solve it by complements. So we're going to look at all the solutions to, all non-negative solutions to this equation without any restrictions, all right? But then we're going to look at several subsets of solutions as well. So I'm going to let A1 be the solutions to this equation where x1 is bigger than or equal to 4. In other words, the first child gets 4 or more candy bars, right? And then let's let A2 be the solutions where x2 is greater than or equal to 4, right? Okay, and then we'll let A3 be solutions where x3 is greater than or equal to 4. And then we'll let A4 be solutions where x4 is greater than or equal to 4. And then again, I'm going to call U the set of all solutions to this equation. So all non-negative solutions to this equation, right? And that's easy to count because we've been talking about that, right, for several weeks. This is going to be 13, and then choose 10, 3. All right. So so this set U, the set of all solutions to this equation without any restrictions except that the variables are non-negative, that's equal to this number. So I'm not going to go back through because we've done that now many times, right? Why all non-negative solutions comes out to be equal to this particular value, all right? But we're going to use that in answering the original question. All right, so once you've defined, right, these subsets of solutions, A1 through A4, I want you to notice that the set of solutions that we're interested in is going to be the intersection of the complements of these four sets, okay? Because the complement of A1, right, the complement of solutions where x1 is greater than or equal to 4 are going to be solutions where x1 is less than or equal to 3, right, okay? And the complement of A2 would be solutions where x2 is less than or equal to 3. And A3 is, the complement of A3 is solutions where x3 is less than or equal to 3. And then the complement of A4 is solutions where x4 is less than or equal to 3. And if you take the intersection of these four complements, that's exactly the set that we're trying to count, right? Because if you intersect the complements of these four sets, you get what? x1 is less than or equal to 3, and x2 is less than or equal to 3, and x3 is less than or equal to 3, and x4 is less than or equal to 3, right? In other words, the number of candy bars that each child get would be less than or equal to 3, and that's exactly what we're interested in counting, right? Okay, so we're trying to count here the intersection of these four complements. But again, just by elementary set theory, that is going to be the complement of the union of the four sets, okay? So the intersection of the complements is the same as the complement of the union. So if we can count the complement of the union, then we will know the complement of the intersections, and we will have the answer to our original question, correct? But it's easy, well, sort of, right, to count the complement of the union, because the complement of the union is just going to be the universal set, right, which is the set of all non-negative solutions minus the cardinality of the universal set, right, minus the cardinality of this union. We've already counted what the cardinality of the universal set is, right? That's an easy set for us to count now. All right, and now we just want to count the cardinality of the union, but that we can do, right, using inclusion and exclusion, right? So we find the cardinality of the union, right, and we subtract that from the cardinality of the universal set, and then we will have what we're looking for, correct? Well, all right, so what does inclusion, exclusion tell us about the cardinality of the union, right? Okay, well, remember, we're subtracting that, so signs are going to change, but here's what you get, right, when you subtract the cardinality of the union. So you're going to, what, subtract the cardinality of the individual sets, right? Okay, and then you'll add back in the cardinality of the intersection of two of the sets, right? Okay, so all possible pairwise intersections, you will add back in those cardinalities. Then you're going to subtract off the intersection of triples of any of the four sets, and then you will add back in the intersection of all four sets at the same time, right? So there's that classic inclusion-exclusion pattern, right? Again, notice the signs are reversed, though, right? Because we're subtracting this union, so we are reversing all the signs in this inclusion-exclusion pattern. All right, so let's see if we can count now the size of these sets, all right? So we know what the size of the universal set is, right? I already mentioned that before. So that's 13 choose 10, comma 3, right? Okay. Now, what about these four sets, right? Okay, the four individual sets, right? What is their cardinality? Well, these cardinalities are all going to turn out to be the same, okay, when you go back and look at how the sets were defined, right? These cardinalities all turn out to be the same, right? And so if you count one of them, you just have to multiply by 4, and you will have, you'll know what all of these are. So let's just count one of them. So what would the size of A1 be? That's solutions where x1 is bigger than or equal to 4, right? Okay. Well, you remember you're distributing 10 candy bars, right? Correct. And if you want x1 to be bigger than or equal to 4, then just go ahead and assign at the beginning 4 candy bars to x1, correct? Okay, so just automatically assign 4 candy bars to x1, and then you have to distribute the remaining candy bars. So that's essentially finding the solutions to x1 plus x2 plus x3 plus x4 is equal to 6, right? Because we've already taken 4 of the 10 candy bars and assigned them to x1. So that leaves us with 6 left to assign. Of course, some of that remaining 6 could go to x1, right? Okay, although we've already put 4 there. But then some of the remaining 6 could also go to x2, x3, and x4. So to count A1, you're simply counting the solutions to this equation. And we know what that's going to be, right? The solutions to this equation. So the size of A1, right, is very easy to count. That's going to be what? 9, 6, comma 3. All right. So I'm not going to go into detail why the number of solutions to this equation is this, because we've talked about that, and I think you know that very well, right? Okay, so actually each one of these sets, right, because they're defined in a very similar way, right, each one of these sets has cardinality 9 choose 6, comma 3. So we'll just subtract that off, right, 4 times. So I'm subtracting off 4 times 9 choose 6, comma 3, right? Now, what about these pairwise intersections of which there are 6 of them, right? 1, 2, 3, 4, 5, 6. So how big are these sets? Well, let's just look at the first one. A1 intersect A2, right? When in A1 intersect A2, that means X1 is going to be bigger than or equal to 4, but also X2 is going to be bigger than or equal to 4, correct? So again, that means the first child is going to get 4 candy bars at least, and the second child is going to get 4 candy bars at least. So before you even beginning assigning the candy bars, right, the Snickers bars, is it Snickers bars? I think so, right? You can go ahead and assign 4 to X1 and 4 to X2. That means then, how many do you have left to assign then after you pre-assigned those 8, I mean? Well, that would just give you 2 left to assign, right? So the size of this intersection is going to be the number of solutions to this set. And again, we know how to count that, right? That's very easily counted. That's going to be 5, choose 2, comma 3. All right, for the same reasons, well, you know how to count the number of solutions to this equation. Okay. All right. Well, so the cardinality of this set is 5 choose. I'm sorry, 5 choose 2, comma 3. Right. Okay. And but these intersections, these pairwise intersections, all have the same size. So just take this number and multiply it by 6, right? And that would give you the sum, right, of all of these pairwise intersections. Finally, now, what about intersections of the triples? Okay, let's take, again, let's just look at one of them. A1 intersect A2 intersect A3, right? So in A1 intersect A2 intersect A3, that means that, X1 is bigger than or equal to 4, X2 is bigger than or equal to 4, but also X3 is bigger than or equal to 4. But if these 3 are bigger than or equal to 4, that's not going to be possible, right? Because remember, when we add all these together, we were only supposed to get 10, right? Okay, because there's only 10 Snickers bars to distribute. So that means that this cardinality is 0, right? And that means all of these, of course, intersections of triples have the same cardinality. They're all 0. And also, then likewise, right, the intersection of all 4 sets, its cardinality also is going to be 0. So we're subtracting all 4 times 0, right, because each of these sets has cardinality 0. And then we're adding back in 0 because this set has cardinality 0. So there it is. There is the, I didn't simplify this, okay? You can do the computations, but there essentially is the answer, right, to how many ways there are to distribute those 10 Snickers bars so that no child gets more than 3 Snickers bars. Okay, all right, so that's a very typical inclusion-exclusion problem. I'm sure you'll have something similar to that on the test. All right, let's look at another one. Number 5. So here now we have a recurrence relation problem, right? Okay, and we certainly have not talked about recurrence relations face to face, right? Many of the other things that we've tested on so far in the class we did get a chance to talk about before the break, but not recurrence relations, or not, well, just a little bit at the beginning of the class, but certainly not in any depth, right? And certainly not solving recurrence relations, which is coming up a little bit later here in the sample test. So you have been having to learn all of this just through the video lectures. That certainly is a disadvantage. And the book's discussion of recurrence relations is not great. Well, it is good, but it's just more complicated than it needs to be for our purposes. So referring to the book is not all that helpful, I think. So you really do have to rely on the notes and the video lectures. All right, so well, enough of that whining there, right? So let's actually solve this problem, because it's not that difficult to figure out. The logic is not. All right, so we're trying to count strings of length n. So our string length is variable here, but strings of length n that, these are bit strings, I'm sorry, so strings that only contain zeros and ones of length n, but we don't want them to contain the string 0, 1, right? So nowhere in our string do we want to have that sequence 0, 1. All right, so we could have 1, 1, 1, 1, 1, all ones, or we could have 0, 0, 0, 0, 0, all zeros, or some other combination of ones and zeros, but we don't want to have embedded in our bit string that combination 0, 1. All right, so let's see how we can write a recurrence relation to count such strings. All right, so so in my answer here, I sort of just wrote down the a recurrence relation, but I didn't explain where it comes from. So because that's difficult to write out in words, but let me explain it to you here now. All right. First, I want to point out though that it's very obvious that S sub 1 is equal to 2, right? And that's because you can just count this by observation. How many bit strings of length 1, right? Remember the subscript here is the length of the bit string. So how many bit strings of length 1 do not contain the substring 0, 1? Well, that's obvious. There are only 2 bit strings of length 1, right? Okay. One of them is 1, and the other one is 0. These both have length 1, right? And of course, since they only have length 1, they cannot contain the substring 0, 1. So of course, both of them count here, right, as answers to our question. So S sub 1 is equal to 2. All right. So that is kind of your initial condition here for the recurrence relation, right? This small value we know, right, by observation, S sub 1 is equal to 2. We could also count just by observation, I guess, S sub 2. That would be strings of length 2, bit strings of length 2 that do not contain 0 or 1. You've only got 4 bit strings of length 2. Let's see, so 1, 1 would be one of them, right? 0, 0 is a bit string of length 2. You have 1, 0, and that's a bit string of length 2. And then you have 0, 1, right? Those are the 4 bit strings of length 2. Those are the only 4 there are. And of course, this one we don't want to count, right? Because that contains the substring 0, 1. So it looks like just by observation we can see here that S sub 2 must be 3, correct? But we don't want to try to count these, all of these instances just by observation, right? That's the purpose of the recurrence relation, right? So once we develop a recurrence relation, then we can count these the strings that we're interested in much more easily, right? By just applying the recurrence relation. All right, now, so let me show you here in general what to do, right? If you have a string of length n, all right, so suppose you've got a bit string of length n, you've got n bits here, right? Okay, so we can think of that as, we've got n slots that we have to fill up with a bit, correct? And but the string's got to start with something, right? Okay, so only 2 possibilities. So it could start with a 1, right? Now, if it starts with a 1, then you can sort of ignore that bit because that is not the beginning of the substring 0, 1, correct? The substring 0, 1 begins with 0, right? So that possible bad substring is not going to begin if it's in your bit string. It's not going to begin at the first bit, right? Because the first bit is a 1. So what that means is then to complete your n bits, you just have to fill up these remaining slots, right, with a substring that doesn't contain 0, 1, right? So you just ignore this, and that means that this remaining n minus 1 bits, right, must be a bit string that doesn't contain 0, 1. So how many such bit strings are there? And the answer is, well, there's S sub n minus 1, right? By definition, correct, right? By our definition in our recurrence relation. So we know that the strings of length n that don't contain 0, 1, right? That's at least as big as the strings of length n minus 1 that don't contain 0, 1, right? Okay. Again, what's the scheme? Take a string of length n minus 1 that doesn't contain a 0 or 1, throw a 1 at the beginning, and then you will have a string of length n, right, that doesn't contain a 0 and a 1, right? Okay, so you know S sub n is at least as big as S sub n minus 1, right? Now, that was the case that your n-bit string began with a 1, but what if it begins with a 0? Well, then you're in a lot more danger, right? Okay, so if it begins with a 0, correct, right? Then that's a dangerous possibility, because that means that if you put a 1 here, then you will have a substring of 0 and 1, correct, right? So that means that this slot must have a 0 in it, because if you put a 1 in here, that would give you a bad string, right? But once you've put a 0 in this slot, that means this slot must also have a 0 in it, correct? Because otherwise, again, you'll have the 0, 1. And that same logic is going to continue until you filled up all, right, of the bits with 0. So if your string begins with 0, there's only one possibility. The whole string must be zeros, right? Okay, all in bits are going to get set to 0 if the first bit is 0. So you have to throw in an extra 1 here. So that's it, right? Strings of length n that don't contain 0 and 1 would be, well, strings of length n minus 1 that don't contain 0 and 1 plus 1. This this string of length, this string of all zeros. So there's the recurrence relation. S sub n is S sub n minus 1 plus 1. And with our initial condition, we know that S sub 1 is 2. By the way, if you use this recurrence relation to count S sub 2, S sub 2 would be S sub 1 plus 1. S sub 1 is 2. 2 plus 1 is 3. So see, that confirms what we had already noticed, right, by observation, that S sub 2 is 3. Our recurrence relation also gives us that S sub 2 is 3. That's a good thing, right? Okay. What about S sub 3? S sub 3 is S sub 2 plus 1. S sub 2 is 3 plus 1 is 4. So we get S sub 3 is 4, and so on and so forth, right? Okay. I think in the problem you were asked to compute S sub 6, it turns out that S sub 6 is going to be 7. All right. So there's the value of S sub 6. All right. So well, there's an example of developing a recurrence relation, right, to solve a a particular counting problem. Let's look at another problem that we can solve with recurrence relation. It's not really a counting problem per se, but it is a nice recurrence relation problem. Okay. All right. So here we have a description of a quantity that we want to determine with a recurrence relation, and then we're actually, instead of just applying the recurrence relation, we're actually asked to solve the recurrence relation. So that means take the recurrence relation and make it non-recursive. So write a non-recursive formula to compute the same value that we're computing with the recurrence relation, and then use that to actually answer a practical question, right? So let's see what's the amount here that we're trying to compute with the recurrence relation. So we're told, suppose a certain investment pays 10% interest each year. So each year you're going to get 10% of the investment added into the investment, right? Okay, so I think you understand simple interest. Now, however, we don't have a huge amount of principal to invest at the beginning in this problem. What we're simply going to do is, as one would normally do, right, we're going to invest a little bit at a time in this investment. So we're going to invest $100 at the beginning of every year, right? At the beginning of every year, we're going to invest $100, right? Okay, and then we want to find a recurrence relation for the total amount, S sub n. So S sub n is going to be the total amount of money after n years. Okay. All right. So it's a little bit tricky to define S sub n, or to think about when S sub n is it's a little bit tricky to decide here when you actually want to calculate S sub n. So let me show you what I did here to make the problem easier to understand in the solution. Actually, I'm going to let S sub n be the investment at the beginning of the nth year. Okay, so I'm going to change there a little bit the definition of S sub n. I'm going to let it be the amount at the beginning of the nth year. So, of course, at the beginning of the 0th year, nothing has happened. So S sub 0 is 0, right? You have not invested any money. But at the beginning of the first year, right? So in other words, when you start the investment, you're going to invest $100, correct? Right? Okay. You're going to invest $100. Right? Okay. So S sub 1, of course, would be 100, right? Okay. Because at the beginning of the first year, we invest $100, and that's all that we have, right, at the beginning of the first year. Now, however, for later years, it's a little bit trickier to determine these values, right? So by inspection, what would S sub 2 be? That's how much do we have at the beginning of the second year, right? Well, notice that at the beginning of the second year, you're going to get paid interest on this $100, right, that you invested at the beginning of the first year, right? So you get 10% of that, plus you add in your additional $100, correct? So S sub 2 is going to be the 100 that you invested at the beginning of the first year times 1.1, correct? Times 1.1, because that's 10% added into this original $100, and then plus the extra 100 that you add in at the beginning of the second year, right? So you get the interest paid on the 100 that you put in the first year, plus the 100 that you deposit at the beginning of the second year. So you can use that same logic here to compute S sub 3 and S sub 4 and so forth, and that easily leads you to this recurrence relation. Okay, so here's the general formula for how much you would have S sub n at the beginning of the nth year. You would take how much you had in the prior year, right, which is S sub n minus 1, right, multiply that by, add 10% of that, right, in other words, multiply that by 1.1. Okay, so that's what you earn in interest from the prior amount, and then add in the $100 that you're investing at the beginning of the year, correct? Right? So same logic that we use to compute S sub 2, just apply it here to the nth year in general, right? So at the beginning of the nth year, right, you pay interest on the prior amount, right, plus your $100 extra that you're investing. So there is the setup for the recurrence relation, right? Okay. So you can actually use that recurrence relation, right? Apply that over and over again to, to calculate how much you're going to have at the beginning of any given year. But part B of the problem says we want to take that problem, right? I'm sorry, we want to take that recurrence relation and we want to solve it. In other words, we want to develop a formula that is not recursive. Okay, so can we convert this recurrence relation into a non-recursive formula, right, where we can compute the amount of the investment at the beginning of any given year? All right, so now we have a problem of solving a recurrence relation. All right, so this is a little bit, unfortunately, this is not a homogeneous recurrence relation, okay? Because notice that in your recurrence relation, you have these recursive terms, well, this one recursive term on the right-hand side, right, of the recurrence relation, but then you have this 100, which is a non-recursive term. So here we're solving a non-homogeneous recurrence relation. All right, so in the notes now we talked about solving non-homogeneous recurrence relations. All right, and so here's how it goes. All right, first you're going to suppose that you have a solution, right, to the recurrence relation that is of the form of the non-homogeneous term in the recurrence relation. Now, I want you to notice this non-homogeneous term does not involve the variable n, it is just a constant. So this is a constant value 100. So you're going to assume that the solution to your recurrence relation, S sub n, is of the form of a constant. All right. In a moment here, we'll solve another non-homogeneous recurrence relation where this non-recursive term is not a constant. Okay. Again, we'll make a supposition about what sort of solution we have, but it won't be our supposed solution will not be a constant. All right. So first, we're going to just assume S sub n is equal to b, where b is a constant. Now, if S sub n is equal to b, right, but it fits this recurrence relation, that means S sub n has got to be, well, this constant, right, b, but it also has to be equal to 1.1 times S sub n minus 1 plus 100, right, okay, right, because S sub n has to match this formula that we're assuming, but it also has to match the original recurrence relation. So S sub n is b, but it also has to be 1.1 times S sub n minus 1 plus 100. But you're assuming that your recurrence relation is constant, right? So that means S sub n minus 1 is also the constant b. So where you have S sub n minus 1, you can also plug in b, okay? So you end up with this very nice equation. B, just ignore this middle part here, b is equal to 1.1 times b plus 100. Now just solve that equation for b. And it does have a solution. We come up with b is equal to minus 1,000. All right, just solve this equation for b. You'll get b as minus 1,000. So that means that our assumed solution to the recurrence relation is minus 1,000. All right, now that's one possible solution to the recurrence relation. Now, what we're going to do is take the recurrence relation, right, this non-homogeneous, so save this for a moment, so put it beside S sub n is equal to minus 1,000, right, so lay that aside for a moment. Now, take your original non-homogeneous recurrence relation, right, and make it homogeneous by striking out the 100 for a moment, okay, so strike that out. And now you have a homogeneous recurrence relation. We're also going to solve this homogeneous recurrence relation. And then the final solutions to the non-homogeneous recurrence relation will just be a combination of the solutions to the homogeneous version and then this assumed solution that we came up with just a moment ago. All right, so let's solve the a homogeneous version of the recurrence relation. And you know how to do that, right? You form the characteristic equation. So take the recurrence relation, set it equal to 0. So just pull the S sub n minus 1, the 1.1 S sub n minus 1, pull that back to the left-hand side. So you get S sub n minus 1.1 S sub n minus 1 equals 0. And that version of the recurrence relation, you can use that to write down the characteristic equation. So here's your characteristic equation. X minus 1.1 is equal to 0. Solve that characteristic equation. That's very easy to solve. That's x equals 1.1. So that means that our solution to the homogeneous recurrence relation is S sub n is equal to some constant, c sub 1, times 1.1, this solution, right, to the nth power. Now, I need to figure out what c sub 1 is, okay, right? And I can do that by using my initial condition, s sub 0 equal 0. All right, so let's see. If this is my, whoops, Oh wait, no. Okay, I'm sorry here. All right, I got ahead of myself. All right, all right. So there is my solution to the homogeneous version of the recurrence relation. All right. Now take the solution to the homogeneous version, right, and then your assumed solution to the non-homogeneous version and combine those, and that will give you your final solution to the original recurrence relation. So we have S sub n is equal to some constant times 1 plus 1 to the nth power minus this 1,000, right? Remember this minus 1,000, which came from our assumed solution to the non-homogeneous recurrence relation. That is the solution that we're looking for. The only thing we have to do to finish this off is figure out what the constant C sub 1 is, and you can do that by substitution. All right, that's where, this is where I was a little ahead of myself a moment ago. That's where you go back to your original initial condition that S sub 0 is equal to 0, right? Okay, see, we know that at year 0 we don't have anything because we haven't invested the $100 yet, right? Okay, so just plug that in to your solution. So plug in 0 for S sub 0, right? Plug in 0 here for n, and solve this equation for C1, and you end up with C1 equals to 1,000. Now you can plug that back in, right, into your solution to your recurrence relation. So there, finally, stuck down here in the corner, there's the solution, the final solution to our investment problem. S sub n is going to be 1,000 times 1.1 to the nth power minus 1,000. Nice, okay? So see, that is not a recursive formula, right? Okay, S sub n does not depend on S sub n minus 1. It just depends on the value of n. If you know the value of the subscript, right, just plug that into this formula and you can compute S sub n. And actually, I did that here on the next page, right, because I'm going to compute S sub 11 using my formula. So it turns out that S sub 11, if you compute that using the formula, you get 1853.12. That means at the beginning of the 11th year, right, this is how much is in the account. So that means the amount after 10 years is this amount minus 100. Why did we take off the 100? Because remember, at the beginning of the 11th year, we put in $100 extra, right? So at the end of the 10th year, just take out that 100 and you have how much is in your account, which is 1753.12. Okay, well, that's a tougher problem because that is, first you have to write down the recurrence relation, right? So that's always kind of tricky. But then what makes it more difficult is you have to solve this recurrence relation, and this is a non-homogeneous a recurrence relation, and those are harder to solve, right? Because you've got this two-step process of finding this assumed solution, finding the solution to the homogeneous version of the recurrence relation, right? And then combining the solution to the homogeneous and then the assumed solution to the non-homogeneous to get the final solution to the recurrence relation. Okay, we'll look at it. I think we have another example of that that I'm going to look at here in just a second. Yeah, right here. Okay, all right, so let's pause here for just a moment, and then we're going to look at, these are very technical questions. We're just going to look at here at solving some recurrence relations. All right, okay. One of them is homogeneous, so that's easy. And then this one is non-homogeneous, so that one is trickier, right? Because it's going to look like problem number 7. But fortunately, it's not in an applied setting, right? So it's just a very algebraic and arithmetic. All right, I'm going to pause for a moment here, though, before we come back and do that. Okay, so let's look at, I think, a fairly easy problem. We just want to solve this linear homogeneous recurrence relation here in 8b. And the reason this is homogeneous, again, remember, is on the right hand side, right, of the recurrence relation, all you have are recursive terms. You don't have any non-recursive terms. So that makes this again, what's called homogeneous, and it makes the solution to the recurrence relation much easier, right? So, like we did in number 7, first take the recurrence relation and set it to 0. All right. Write it like this. Still the same recurrence relation, right? I'm just rearranging terms here, right? So you have s of n minus 6 times s of n minus 1 plus 7 s of n minus 2 equals 0. And then from this, right, you can derive what's called the characteristic equation, which would be which would be x squared minus 6x plus 9 is equal to 0. And it's that characteristic equation that's really the key to solving the recurrence relation. So let's switch back over here to the answers, right? Notice in the answers, where's the answer for this one? Yeah, right here. I've started the answer already with the characteristic equation, because that's really the key step there of writing down that characteristic equation is really the key step, right, for solving the recurrence relation. And then, so you have x squared minus 6x plus 9 equals 0, and then solve this equation, right? You may have to solve this using the quadratic formula, but here we get lucky because this equation, the left-hand side factors, it's x minus 3 squared, and so you get one solution, only one solution to the characteristic equation. It would be a little bit easier if we had two solutions to the characteristic equation, right? But with only one solution, here's how you write down then your solution to your homogeneous recurrence relation. It's going to be C1 times this root, right, raised to the nth power plus a second constant C2, also times the root raised to the nth power, but because you only have one root here instead of 2, you have to throw in this additional factor of n. So you can distinguish these two terms, correct, right? So if you have two roots to the characteristic equation, you just write C1 times the first root to the nth power plus C2 times the second root to the nth power, right? But with only one solution to the characteristic equation, you have to write the second constant C sub 2 times n. This factor n is thrown in times the root raised to the nth power, right? Okay, so that is the solution to the characteristic equation. But now we want to figure out what these constants C1 and C2 are, right? So that we can fill them in. And this you do by using your initial conditions to the that you're given for the recurrence relation. Here we were given that S sub 0 is equal to minus 2. But S sub 0, of course, we can also compute by this formula. So when you plug 0 into this formula for n, you get C1 times 3 to the 0th power plus C2 times 0 times 3 to the nth power is equal to minus 2, right? And then just solve that equation. You get C1 is equal to minus 2. Then, then you do this same thing for the second initial condition. You plug in 1 for n right into your recurrence formula, but you also know that you're given that S of 1 is equal to 2, so you end up with this equation, 3C1 plus 3C2 equals 2. But you already know from this first initial condition that C1 is equal to minus 2, right? So substitute that, solve for C2, and I think we get that C2, if I did this right, we get that C2 is equal to 8/3, right? So there you know what C1 and C2 are, and so you can fill them in, and so there's your final solution for the recurrence relation, all right, with the correct values for C1 and C2 filled in. All right, now let's look at the non-homogeneous case, though, right, because that's the one that's a little bit more involved. So let's look now at 9a, right, okay? So here, this is not a homogeneous recurrence relation, because on the right-hand side, right, of the recurrence relation, you have this recursive term, 3 times s of n minus 1, but the problem is you have these non-recursive terms here, right, the n minus 1, and that means the recurrence relation is non-homogeneous. All right, so we're going to go through kind of the same steps we did in problem 7 to solve this one, right? So what do? look at the form of your non-homogeneous terms, right? N minus 1. That is a linear expression in the variable n. Okay, so you're going to assume that you have a solution that is of a linear form in the variable n. So that's what I did first here in 9a. We assumed that S sub n is a sub n plus b, because that would be a linear expression, right, in the variable n. Now, you assume that solution, but you have to now compute what a and b are, right? So that's where the recurrence relation comes in, right? Remember, the recurrence relation is S sub n was equal to 3 times S sub n minus 1 plus n minus 1, right? So S sub n, though, you're assuming is a sub n plus b. What's S sub n minus 1? That's going to be the same thing. It's going to be a times n minus 1 plus b. Remember, you're multiplying all of that by 3. So see, all of this is S sub n minus 1. And then, of course, plus the n minus 1 at the end. That's a part of the recurrence relation. So, so now you have to use this equation to deduce what a and b have to be. And you do that by comparing like coefficients. So simplify the right-hand side of this equation. Keep the a n plus b on the left-hand side, but simplify the right-hand side, right? So gather your n terms together, and then gather your constant terms together. And then equate coefficients. See, on the left-hand side you have a times n. On the right-hand side you have 3a plus 1 times n. So that means a is 3a plus 1. Just solve that equation and you get a is minus 1/2. Now, what about for your constants? Well, here you have minus 3a plus 3b minus 1. On the right-hand side, this is your constant, but on the left-hand side, your constant is b. So that means b is equal to minus 3a plus 3b minus 1. But you already know what a is, right? A is minus 1/2. So substitute that and then solve for b, and you get b is minus 1/4. So a is minus 1/2 and b is minus 1/4. That means your assumed solution is going to be, right, minus 1/2, that's a, times n plus b, which is minus 1/4. So there is my assumed solution, right, to the non-homogeneous recurrence relation. Now, go back to the recurrence relation, as I mentioned, right, and take out the non-homogeneous terms and solve the homogeneous version of the recurrence relation. So I'm going to scratch out the n minus 1 and just look at S sub n equals 3 times S sub n minus 1. That is homogeneous, right? When you strike out the non-homogeneous terms, right, of course you get a homogeneous recurrence relation. There is its, there's what we get when we set it to 0. So the characteristic equation is x minus 3 equal 0, right? Okay. Solve that recurrence relation, solve that characteristic equation, you get x equals 3. So here is the solution to the a homogeneous version of the recurrence relation. It would be S sub n is c1, some constant, times this root, right, raised to the nth power. Now, take that solution and combine it with the assumed solution here, right? Minus 1/2 n minus 1/4, and that gives you your final solution to the non-homogeneous recurrence relation, except we don't know what the value for C1 is, right? But you can find that by substitution, because you know from your initial condition, right, that S sub 0 was supposed to be 1. So plug 0 in here for n, set that equal to 1. That's what I did on this line. And you end up getting, very easily here, C1 minus 1/4 is equal to 1, which means that C1 is equal to 5/4. So C1 here is 5/4. So just plug that back in for C1, and that's it. That gives you your final solution to the recurrence relation. S of n is 5/4 times 3 to the nth power minus 1/2 n minus 1/4. See, that is non-recursive, right? Okay, because it doesn't have a recursive term on the right-hand side. Okay, well, those are the problems that I wanted to show you. I know solving those non-homogeneous recurrence relations is a bit challenging there, right? Okay. Remember, also remember, it's even worse than it seems, because the solution method that I'm showing you here for solving non-homogeneous recurrence relations does not always work. It works sometimes. It works in these problems, but sometimes it doesn't work. In general, there is no all-purpose solution to finding solutions to solving non-homogeneous recurrence relations. That's actually a very difficult problem in general. All right, so that's it for me talking this semester. We've reached the end of the semester. In terms of the lecture, we just have our test left to take, right? Okay, so our test on Monday, and then I hope everyone will do well on that, and then so you won't have to feel compelled to take the final exam, right? Unless you want to. Okay. But that depends on your grades, right, on your midterm test. So the test will be posted by, probably by the time you see this videotape, you'll be working on it. So make sure you get those back to me by Wednesday at 1 p.m. And then if you want to turn in your homework number 7, you can also turn that in on Wednesday as well. You can have to, you don't have to turn that until midnight on Wednesday, however, okay, if you want to submit it to improve your homework score. All right, guys, as usual, stay safe, right? Things are dragging out a lot longer than I had hoped with this coronavirus, but it looks like at least some of the restrictions are going to get lifted soon. Okay, but but even when those restrictions are lifted, right, be sure that you are being careful. Correct, right? So wear a mask. I think that's helpful, and of course, as always, wash your hands. All right, so. I may not be talking at any of you again, but if you need to speak to me, be sure to log on to my Zoom office hours. Oh, remember, by the way, at the end of the semester, so I need to post more information about that. Remember, you've got this pass-fail option at the end of the semester. So at the when you see your grade, your letter grade, your final letter grade after the final exam. Remember, if you do not want to keep a letter grade, you can contact me and switch that to a S or a U, right, which will not factor into your GPA. So an S would give you credit, but it wouldn't count in your GPA. A U, you would not get credit for the course, still would not count in your GPA. If you take a letter grade, that's going to count in your GPA in the usual way. I'll send more information about that. I know that's been posted in all of your courses all over the university, so I know you're aware of this, but just to remind you of that. Okay, all right, so take care. Good luck on the test.